Hey y'all. So we are back with part two of the data frame manipulation lab. So part one was all about how to select and filter and summarize, so sort of performing basic data operations on a data frame that you read into R using the tidyverse package and its sub packages. So part two builds on that with a couple more advanced features. And so what we're going to talk about is ways to use conditional statements in creating new variables. So sometimes you want to apply some operation to certain values and not others, or you want to create some sort of new aggregated version of a data frame. So you want to say, or a column. So you want to say if a value is greater than this, then assign this value. If it is less than that, assign a different value, right? So building in like if then sort of functionality into your variable creation. Next, talking about how to actually join data frames together. And then finally getting into what we touched on briefly last week in spreadsheet practices about wide versus long data frames and actually practicing changing data frames from wide to long and back again. So where we're going to start is by, again, loading the tidyverse package. So use the library function, library, and then type tidyverse in the function call. And so this is going to attach the tidyverse package. And then we're just going to keep working in the same data frame that we've been practicing on thus far, the mammal, the 35,000 mammal sampling or monitoring observations or whatever those are. So again, we're going to call this object surveys, surveys, and use the read, and I'm just going to use the read.csv. Actually, we'll use read_csv to stay consistent with the tutorial here. So read_csv, which again is the tidyverse version of read.csv, functions much the same. And again, we're going to find this data frame or the CSV file in the data subdirectory of your class R repository. So data slash, and then the object is going to be called portal, or sorry, the file name is portal_data_joined.csv. So again, the full file name is data/portal_data_joined.csv. We're going to put that all in quotes because you tell R how to find files as string values that show the file location. So read CSV, it's going to read that in, give us a whole bunch of other information about that data frame we just read in, but we can call str on it like we often do, and it will show us all sorts of features. So it shows us the column names, it shows us the variable types, somewhere it shows us the actual number of rows and columns. You're familiar with this already. Okay, so next what we're going to do is practice conditional assignment. And so the example shown in the tutorial is hindfoot length. So I guess that's the rear foot of all these rodents. So if we use the summary function on that value, and so Liza last week showed us how we can start with the data frame, use the $sign, and then type the name of the variable. We want hindfoot length. And that essentially just pulls that specific vector out as a unique vector in R. We're going to summarize that vector. So run the summary function, and it shows us the minimum value, the maximum value, the number of NAs, the median. So for instance, the medium hindfoot length is 32. I assume that's millimeters or centimeters. I don't know how big a rodents we're talking about. Anyways, that doesn't matter. So let's say you wanted to create a new variable that essentially grouped these observations in terms of large or small hindfoot length. And so what you might want to do is pick a value, in this case, the mean value, 22.29, and say anything below that is going to be classified as small, and anything above that is going to be classified as large. So the base R, and what I think is frankly the easiest way to do that, is to use a function called ifelse. So ifelse is a special function that has essentially taken essentially like condenses a longer if-else call in R. You could also type if this, else that, and so on. And we'll show you how to do that at some point when we learn to build functions. But in this case, you can just call the if-else function. And again, as always, if you want help in using that, if you put a question mark in front of the if-else function and run that, what will show up is the help file. In this case, there are three parts to the if-else function. There's some sort of test, the if test, and then there's two responses. One, what do you want R to do if yes? And two, what do you want R to do if no? So again, test, comma, yes, comma, no, is the format of the if-else function. So recall that in this case, we want to say that if surveys hindfoot length, so that's again, the hindfoot length vector from the surveys object is less than the mean, and the mean was 29.29. Although actually we can hard code that, can't we? Or sorry, soft code that. So let's actually say mean surveys hindfoot length. So what I've done here is now we're saying if the value in that vector, if any of those values is less than the mean value of this vector, we do have to remove the NAs, so na.rm. So again, this test here is we're comparing each hindfoot length observed to the mean value of hindfoot length, and we can verify that it's a many to one comparison, because if we simply call mean on hindfoot length, we get that one value, 29.28793. So essentially now what we're saying is if the value is less than that mean, we want R to assign a value of small. And then if it is bigger than that, we want R to call that big. Again, reviewing the if-else function construction, we have the test. Is this less than that? What to do if yes, call it small. What to do if no, call it big. So we can run that, and actually now what we get is a whole vector of smalls and bigs and then some NAs. So you can probably guess that the NA values show up where there's an NA value for hindfoot length. So if you feed an NA into that if-else statement, R says, well, I don't know what to do with this, so NA in, NA out. So we get bigs, smalls, and NAs. Part is you can nest all of this within a mutate call to that data frame. So now if we say mutate that surveys object, data frame object, and in this case, we want to perform, let's just copy it because it was a lot of typing. We want to create that same if-else statement. And remember, if we don't assign a column name to the new column we're creating using mutate, we get the entire sort of wonky function call as the name. So let's say input size is our new variable. And if we run that, oh, not printing well because there's too many columns. So let's go ahead and say, let's overwrite. So in this case, we're going to overwrite the original surveys object using mutate. So in this case, we're saying take the original surveys object, run this if-else statement we've created, and create a new column called hindfoot size, and then overwrite everything so that the real surveys object has that hindfoot size column. And now if we type surveys $hindfoot _ size and run that, we can see that now there is a new column in that data frame that has small and big and NA values. The tutorial teaches a tidyverse version of this that is a function that's called case when. I actually really don't like the case when function. So if Liza prefers that to if else, I will let her sort of champion that in class. My reason is that case when doesn't handle NAs as nicely as the if else function. So you actually have to explicitly tell case when how to handle NAs, whereas the if else function simply automatically handles it. And so if else is base R, it's a really basic approach that very intuitive test, if yes, if no, format I think is really convenient. And so for my purposes, I would recommend just learning if else, but there's definitely guidance in this tutorial about how to use case when instead if you prefer, but I'm going to go ahead and skip over it. So go ahead and take the challenge. In this case, you're going to read in the iris data frame and perform a slightly more complicated if-else statement. And so the challenge here, and this is ultimately why case when is created, is that if you use if-else, you have to use a series of nested if-elses, and case when allows you to sort of specify multiple values within that call. And so we can talk about that in the challenge again, but it's sort of a trade-off of what's happening with those NAs. Okay, so moving on from conditional assignment. Next, we're going to talk about joining. So joining it's probably something you've at least had some experience with, even just in Excel. And it's ultimately typically a task that's super important for most research and practice, right? Because a lot of the value add of new and novel research is you're taking some original data or some data and combining it with new data or two new data sets and making it something that is bigger and more powerful. And so a really important tool, also ultimately really important to understand what's happening when you're doing joining, because it's very easy to run some sort of join, you get some result out, you analyze those data, but if something went wrong in the join or it didn't join correctly, that can be a source of major pain and heartache. So definitely important to make sure you're familiar with the functionality of the joining, both in dplyr and in other packages you might use. So first thing, we've already loaded in the surveys data set. Let's load in a second data set from our course example data. So this one is called tail length. And so we're going to, let's just call the object tail and make that caret sign to assign the object. And we're going to use the read underscore CSV function. And again, all our example data live in the data subdirectory of your class repository. So you're going to type data / and in this case, tail underscore length.csv. Put that all in the quotes. So it's a string or character object, and run that. And now we have a new object right in called tail. And you can run str on that to see that it has 34,786 rows and 2 columns. So a little bit simpler data frame. You can probably picture what's going on here already, as we have these two about 35,000 row sets, and we're going to merge them together. Okay. So the tutorial shows calling summary on the record ID column, which you're welcome to do. But in this case, it's probably pretty intuitive that there's a reason record ID and record ID are in both data sets, and we're going to join them. But what you can see if you call summary is that the two values are identical. And so if you call summary on tail $ record ID and run that, and then summary on surveys $ record ID, sure enough, it turns out that we have identical record IDs in there. And so this should be a pretty clean and straightforward join. So basic structure of join functions, and we're going to talk about join functions rather than singular join function, because dplyr provides multiple ways of joining. And so it's always going to follow a fairly common format, which is simply like first data frame or table, second data frame or table, and then some sort of denotation of what to join with or by. And then all the functions work that way. And so there's 4 basic functions that are helpful to know for joining using dplyr and the tidyverse. The first one is inner join. And so what inner join does is it returns all rows where there's a match from both values. So if you're merging A and B, an inner join says return only cases where there's a match, a common ID in A and B. In contrast, left join and right join keep everything from one side and only the matches from another. So if inner join keeps only the ones that have a match in both, left join says return everything in table A, and then only the cases from B that have a match in table A. And so what happens then is you get everything in A, you get all the matches from A to B, and then if something in table A doesn't have a match in B, those values get coded as NA. So in this case, we have tail length recorded in data set B. And so what would happen if we did that left join, if something was in A but not B, then tail length would be coded as NA. Right join does the exact opposite, right? And so you could just move those around functionally. It doesn't really matter if you could accomplish anything with left join simply by flipping what's table A and B without ever using right join. They're simply the inverse of each other. And then full join returns everything. So full join says whether or not there's a common match between A and B, I want you to return all rows and assign NAs in any case where one variable isn't observed in the other. And so full join is sort of like the lossless way to join. You can probably already think about how this stuff gets a little wonky if IDs aren't unique, and that's where a lot of things can go kind of crazy here. So like in our example data frame, we've created examples where there's only one ID per observation. Each ID in each row is unique. You can imagine if you had recycling of a common ID number, it's observed multiple times, something like that. Once you get into like many to many or one to many joining, things get a little more complex. But in this case, because we only have unique identifiers that are used once in each data frame, we have one-to-one joining. And so the behavior is a little more predictable. Let's give it a shot. Okay. So let's start with the left join function. So we're going to make an object called surveys underscore joined. That caret to assign that object. And let's call the left join function left underscore join. So we're going to start with the A table, surveys, and then the B table, tail. So surveys, comma, tail. And if you look in within the function help package, or you type tab or read it all out, you'll find that you could hard code that, or hard code is not the right word. You can specifically code it. You can say, I want the X data frame to be surveys, and I want the Y data frame to be tail, but the function works just fine if you just insert data frames A and B as the first and second calls. And then in this case, we know we want to join by record ID. And so we're going to type by equals record ID in quotes. And so in this case, we have that column name in quotes. And so this is a little bit of a confusing thing that simply takes practice when you're using dplyr to remember which is which. So if you recall, when we used the select function, if you wanted to select record ID, you would just type record ID without putting it in quotes, and R would return the column record ID. In this case, you have to use record ID in a string. I'm not totally sure why that is, but it is the way the function worked. So in any case, if we run that, now we have this combined survey, and we can call str on surveys joined, and we see that, or we observe that the last column is now called tail length, and we have combined those two data frames. The number of rows hasn't changed, right, because it's that one-to-one join. We have every observation we originally had from A, and then any tail length observations that match from B. One feature to note, and let's see how this works here, is sometimes if you call join and you don't specify any variables to join on, and you simply run left join survey comma tail, the join will still work. And the reason that is that dplyr is smart enough that when you ask it to join, it will actually look through and say, are there any common identifiers in these two data frames that we can join on? Oh, in this case, these two columns are both identically named record ID. That must we want to join on. It'll go ahead and do it. You want to be careful with this because that's powerful, but there's certain cases, right, where two IDs are not the same, even if they have the same title, or you simply don't want to join on those identical column names for whatever reason. And so typically, in this case, it's often best, unless you're very confident about what all the column names are and what they represent, to not just let R automatically pick how the join works and actually specify using character strings which columns you want to join on. Okay, so the additional part of this, the tutorial about joining talks about adding, modifying the by argument and creating sort of different ways of filtering and then adding some joining and things like that. So I'll go ahead and leave that for class. You can see what we did here is we used the filter function to filter certain species. And then when we joined, we got more interesting behavior because there wasn't what existed in B and A was not identical, right? So instead of two, like 34,700 row observations one-to-one, we had a case where we had a much shorter data frame where the entries in A were in B, but not all the entries in B were in A. So there wasn't that sort of reciprocation. And so helping you explore sort of more interesting joint behavior. All right, next thing we're going to bounce on to is reshaping. So we talked a little bit about this during spreadsheets week. So I'm going to skip over this overview and simply go down to actually using the functions. So the two functions that we're going to use in class are pivot underscore wider and pivot underscore longer. And so they do exactly what they say. One takes a data frame, makes it longer. One takes a data frame and makes it wider. They can both be found in the tidyr function. And so before this, we've been working in dplyr for joining and selecting and filtering. In this case, this is tidyr. And as always, you can learn more about these functions using the help files, always recommended. So here's a quick overview of how they work. So pivot wider, and type that out, pivot underscore wider takes three core entries. So the first entry, and this is sort of common to a lot of tidyverse functions where we're doing data manipulation, is the data frame. So in this case, we want to manipulate the surveys data frame. So we have that here. And so surveys data frame, we're going to enter a comma, and then the next entry are the names of the columns we want to spread out. followed by the names of the columns we want to take the values from. So what does that mean? It means that we have some column where we want to extend it, right? So take this table and make it wider, and then some column where we want to actually take the numbers and insert those in those new wider columns. So here's an example. What we've started with here is we've created a new surveys object, and so in this case, surveys underscore MZ, and we've performed a set of piping and filtering on it such that we have ended up summarizing new average weight values for each species. And so just to save your time, I'm going to go ahead and copy this in and run it. And then if we take a look at the surveys MZ function, if we run that, what we have here is we have a data frame that has a one row for each combination. I guess it wasn't species, my apologies. Each combination of genus and plot ID, so like where the sampling happened, and the mean weight for each of those combos. And so it's 196 rows of 3 columns where we have some unique genus plot ID value and then the mean weight. And so what we're interested in doing here and making this wider is spreading those values out. So we're going to end up with fewer rows and more columns. If what the tutorial shows is ways of actually looking under the hood and figuring out sort of how many unique values you have. Excuse me. Oh, sneezy. And so in this case, what we're able to find is that if we call unique on surveys MZ genus, we have 10 values, or you can use the tidyverse function n distinct on that same surveys underscore MZ genus vector, and it'll give you the number 10, right? So we went over like 5 different ways to do this the other day in class. In any case, now we know we have 10 unique genuses, and so we want to create a data frame. In this case, that's wide, and then it has 1 row per genus, and then we're spreading out the plot ID columns. And so what this is going to look like now is 10 rows, 1 for each genus, and then 1 unique column for each plot ID, and then the values we want to be in there are going to be the particular mean weight value that corresponds to that genus plot ID combination. So if we're using the pivot wider function, and the example here shows the example in the code in the tutorial uses piping. I'm just going to call pivot wider first, just so we can kind of go over what all the entries are. So pivot underscore wider. First entry is our data frame. In this case, that modified surveys underscore MZ object. And then what we want is the first entry, the names underscore from, oops, I typed form, equals plot ID. So those are this is how we denote the rows that this is how we denote the columns we want to spread out over. So what we're saying is take that plot ID column, and for each unique observation you see of plot ID, turn that into a different column. So plot underscore ID. And then the values from entry, this third entry, is where we say, here's where to find the numbers to fill into those new column row observations. So in this case, mean underscore weight. So again, 3 entries, the data frame, the names to take from, the values to take from, and oh, they gave me an error. Why did it give me an error? Oh, give me an error because I typed value from instead of values from. So a good, simple, fun R error, and actually it looks like dplyr was smart enough to really tell me what the issue was. It said you have a problematic argument value from. So values from, let's rerun that call. And so what results is a modified data frame or tibble that now has 10 rows, and it has 25 columns, because in our data set, there was 25 different plot IDs that were observed. And so we can save that as a new object. We'll call it wide underscore survey. Store that object. And if we call dim on wide underscore survey, it will sure enough say, hey, 10 rows, 25 columns. We can call str just like on any other data object. And it will print out the names of the columns and the rows and all the other data structure stuff we might be interested in. Okay, so that's pivot wider. You can probably guess, given that, how pivot longer works. So in this case, it's essentially doing the opposite, right? And so we're taking some sort of wide data frame, we're going to create more rows instead of more columns. So what's happening here now, and if you think about it, there's one additional challenge to going from wide to long than there is from long to wide, in that if you want to collapse and make more rows and fewer columns, you have to select multiple columns you want to collapse on. And so that adds a bit of complication. So in pivot wider, there was only 3 entries to that function: the data, the names you want to take from, and the values you want to take from. In this case, there's a 4th entry, the columns you actually need to pivot in order to make the data frame long. So let's dive in and you'll see what I mean by this. Okay, so we have that wide survey object we just created, and now let's take it and remake the, see if we can replicate the original survey object using the pivot long value. So again, the example code shows piping, and you're welcome to use that, but I think just for simplicity here, let's just call the pivot longer function. And we know that the first entry into the pivot longer function needs to be whatever data frame we want to pivot. And so in this case, the wide survey data frame is the first entry. And we know that there now has to be 3 more entries. So I'm actually just going to type a couple other commas there, so I know I have to fill in each of those spots. So second spot in the pivot longer call is the actual columns we want to pivot on. And so in this case, there's a couple things to denote. You can use a minus sign, or simply call, what's the best way to describe this? Sometimes you want to tell, in pivot, you want to say ignore this rather than actually pivot with this. And so in this case, that's actually what we're going to do, is we're going to say we want to pivot all of the columns except for the column genus. And so if you think about it, that's convenient in this case, because rather than saying, you know, I want you to take plot 1, plot 2, plot 3, plot 4, instead you're doing like inverse sorting, where you're saying, I want you to take every plot that's not called genus. And so the simple way this function allows you to do that is you type minus genus as the value. And so it's essentially saying, I want you to plot to pivot on all the ID columns that aren't called genus. Okay, next entry then is we still have to have the names to and the values to. And so if you recall, in pivot wider, we said names from and values from is what we're taking from. In this case, what you're saying is, what do you want to call the new names column, and what do you want to call the new values column? And so in this case, we know that we want the the name of the column to be plot ID. So names underscore 2 equals plot ID. And we know that we want the column of values that we're pivoting to be called mean weight. So values 2 equals mean weight. So now we have 4 entries to this pivot longer function. We have the original data frame. We have our inverse column selection. So in this case, saying pivot all the columns except for genus. We have our names to, so saying the new column you're creating, call it plot ID. And the values to, saying the new values column you're creating alongside the names column is mean weight. So let's do a quick piping call to head here. So again, the piping function, percentage sign greater than percentage sign, and then simply the head function. And so when you run that, what results is a replication of our original 3-column genus by plot ID weight summary, where we have 1 column for genus, 1 column for plot ID, and 1 column for weight. So we've preserved that original genus row filtering. Now we've pivoted, so we have plot IDs going down in row instead of across in columns, and then the weights go down in row next to the plot IDs. The course tutorial walks through the reasoning for why, because of NA values, you end up with different shapes when you pivot back and forth, depending on how those NAs are treated. And so in this case, you end up with fewer rows than you end up with more rows than we started with. So the reason for that is, you can imagine when you pivoted wider, what happened when there was a case where there was no weight value for a particular plot ID for a particular genus. And so essentially, if you picture like that matrix, NAs were filled in where there was no observation. And so then when we melted that into a long data frame again, it simply took that NA value and kept that as a mean weight for a particular genus plot ID that was unobserved. And so you end up with both observed and unobserved values in that long data frame. Not really a problem, just to be aware of sort of if you ask, if you make a data frame wider, you're creating this matrix that has both observed and missing cells. And that's actually one advantage of the long data storage format, is it's essentially much more, it's more storage friendly in terms of it doesn't store any, it essentially acts like a sparse matrix. It doesn't store any unobserved values. Okay, so go ahead and check out the challenge, pivot wider, pivot longer, try some joining and let us know how it goes, and we will go over this in more detail in class. All right, thank you.